So, I'm going to record the last few videos for discrete mathematics. This is still section 2.3. When dealing with finite sets, remember I defined this idea of cardinality back in section 2.1. Let me pull it up here. Yeah, here are my notes. If a set has exactly n distinct elements for some natural number n, then it's a finite set. So we're talking about something the size of that set is a finite number. When dealing with finite sets, you can represent a function between those sets by using a thing called an arrow diagram. It's a super simple idea. It's just like you can list the elements of the domain on one side and list the elements of the codomain on the other side, and then draw an arrow from each domain element over to a codomain element. So, for example, if my set A, my domain is 1, 2, 3, and my codomain is one of my favorite sets here, XO square triangle, then I can map 1 to anything I want. I'm basically just drawing the map, right? Let's say 1 maps to square, right? And then 2, let's say 2 maps to X, and 3 maps to triangle. Then, I could say like f of 1 equals square, for example. And so I just follow the arrows. And I can do that however I want, okay? I just have a few different examples here because I want to make some points. I want to make some points about that. So you notice in the first example here, my domain has 3 elements and my codomain has 4 elements. So the way I drew this map, circle was left out. Poor circle. Circle is in the codomain, but not in the range. Okay. So, that was just the way I happened to write this. Now, let's see if I can do this differently. Maybe I can do it some other way that will make it so that none of the elements are left out. Can I do that? Well, let's just do something simple. Let's have 1 map to X, 2 map to circle, 3 map to... Oh, well, I can have 3 map to square, but then now my triangle is left out, right? Well, how can I fix that, right? Can I get it so that everything is mapped to? Is it possible to make this function surjective? Well, not really, because once I've mapped my three domain elements to 3 codomain elements, the best I can do is have them map to all different things. But there's still going to be 1 codomain element left out, no matter what I pick, right? I can't have 3 mapped to more than one thing, for example. Like, that's not allowed, right? That would not satisfy the basic rule of being a function, having unique outputs. So you can tell there's a bit of a situation right there where it's really impossible for me to make a function here with this domain and codomain. It's impossible for me to make a function that's surjective. Well, let's look at this next situation. Actually, let's jump over to the third one here. For the third one, I have 5 elements in my domain this time, and still 4 elements in that codomain. So let's map some things. Let's have 1 map to X, 2 can map to triangle, maybe 3 maps to circle, 4 maps to square, and then where does 5 map to? Well, it's got to go somewhere, right? It's got to go somewhere because every domain element has got to go somewhere. So where is it going to map to? Let's say it maps to triangle. But now, as you can see, I have 2 things mapping to triangle. It was easy to make this function surjective, right? It's easy to make it surjective. It doesn't have to be. It doesn't have to be surjective. It could have been that maybe 1 maps to circle as well, right? And then maybe X here is going to get left out. So it doesn't have to be surjective, but it certainly is easy to make it so. Right? Because I have plenty of domain elements to work with. But in this case, in this situation, what I can't do is I can't make it injective. It's impossible to make this function injective because, as you can see, if I was trying to make it 1-to-1, remember injective is the same as 1-to-1. If I was attempting to make it 1-to-1, I would map the first 4 elements to all 4 of these elements separately, 1-to-1, and then I would come to my last element and say, well, where does that one map? Like I said earlier, it's got to go somewhere, and wherever it goes, you're gonna end up with a situation where 2 inputs are mapping to the same output. So that is not 1-to-1. So far we've learned here this situation with this particular domain and codomain. This is guaranteed to be not surjective, and with this situation, this is guaranteed to be not injective, right? So what if I have the same number of elements? well, I can make whatever function I want here. I can make it up. So I'm defining my function by where the arrows go, right? So let's say I could go like this. I could have everything mapped to x, right? So it's possible to do that, right? Like, so that's not injective, and it's also not surjective, right? That's a valid function. But at least if you have the same number of elements in the domain and codomain, it's now possible to map my domain to my codomain in such a way that it ends up being both one-to-one and onto. So it ends up being both injective and surjective. So that's possible in this scenario. So there's something special going on here, all right? Having shown you these examples, I want to then bring up a theorem. So there's a theorem that basically takes what I've shown you here and takes what we've learned from exploring this, and it kind of makes it sort of official. So let's say let A and B be sets. All right. There's two statements. One, if there exists a function f from A to B that is surjective, so it's onto, it maps onto the entire codomain, well then we mustn't be in this situation. We can't be in this situation. We might be in this situation or this situation, right? But this is the one that is not surjective. So what I can say for sure is that if you take the if you look at the cardinality of the domain and codomain, we're either in this case or this case. This is when the domain and the codomain are the same size. This was when the domain was bigger. So this should be greater than or equal. That's what you can conclude, okay? And equivalently, if we take the contrapositive of that, it's equivalent to say if the cardinality of the domain is strictly less than the cardinality of the codomain, then any function you make, f from A to B, is guaranteed to be not surjective, okay? This first statement I wrote was P implies Q, and the second statement is not Q implies not P. So this is exactly what I was saying over here, right? That when you have a smaller domain than codomain, you can't make a surjective function because it's impossible to map to everything if you don't have enough elements to work with. So that's the first thing. So now the second thing, you can probably guess where this is going. I bet you can guess, if you can think about what I said about number 3 here, and you can probably figure out exactly what I'm going to write. It is, if there exists a function f from A to B that is injective, well, if it's injective, then it means we can't possibly be in this scenario, right? So we can't be in the situation where we have a larger, A is larger than B, right? Let's write out the inequalities between the cardinalities there, just to remind us. So we can't possibly be in that situation. So we must be in one of these two, which means that the cardinality of A is less than or equal to the cardinality of B. And then equivalently, if you take the contrapositive of that statement, contrapositive, here we go, we could write if the cardinality of A is greater, strictly greater than the cardinality of B, right? Remember, A is codomain, A is going to be our domain and B is going to be our codomain, right? Then any function, f from A to B, is guaranteed not injective. All right, so this theorem establishes this kind of relationship, this kind of connection between the idea of injective and surjective functions, and also connected to the idea of cardinality and like the relative size of the domain and the codomain. If you wanted to prove that the domain was smaller than the codomain, what you could do to prove that is you could prove that like there does exist. Let's see, if you want to prove it's smaller, you could prove that there does exist an injective function, but maybe that there doesn't exist. There can't possibly exist a surjective function, right? Or hang on, let me think about that. I wasn't planning on saying this, and I think I said it wrong. This is kind of off the top of my head. If you want to prove that something is, if you want to prove that A is smaller than B, like has a smaller cardinality, then you would show Yeah, I think I said it right the first time. You would show that there exists an injective function, but there can't possibly exist a surjective function. How do you prove there can't exist a surjective function? Well, you might assume that there is one, and then, prove that that leads to a contradiction. Proof by contradiction is super useful in scenarios like this. Yeah. So anyway, so this is a pretty important theorem. We're going to work with this theorem more in section 2.5. I had to think about that for a second. 2.5. The last thing I want to leave you with in this video is a corollary. A corollary that follows up right after this theorem is immediate consequence of this, which has to do with this special situation here in the middle, and that is the cardinalities of A and B must be equal, actually, if and only if there exists a function f from A to B that is bijective. So a bijection, which remember means that it's both injective and surjective, right? If you can find an injective function, it means cardinality of A is less than or equal to cardinality of B. If you can find an injective function. If you can find a surjective function, it shows that cardinality of A is greater than or equal to cardinality of B. If you have both of these things at the same time, both less than or equal to and also greater than or equal to, well, you must actually have equal to. So a function that is bijective proves that the domain and codomain are the same cardinality.